good afternoon, everyone. So we'll start our first afternoon session about Protostar objects. So our first speaker is Shigehisa. So he will talk about his study about the proto-binary with pole. Yeah.
Okay, my name is Takakuwa from Kagoshima University in Japan. I was a faculty member here as 7 years ago under Paul. So I don't know how to give my talk after that. It's kind of difficult, but I try. So I will talk about our series of SMA and ALMA study of proto-stellar binaries in a individual region. This photo is a volcano Sakurajima with some Shinko Bay. It's a very nice place. Please visit Kagoshima. My name is start with introduction. Binary formation. So, as you know, solar type binary is more than 50%. So, binary star formation is critical for understanding the formation of solar type stars. And I checked that more than 150, 170 exoplanets around binaries. So binaries are also important in planet formation. Then we studied two key parameters. One is circumbinary disk, which act as mass reservoir for the protostellar binaries. And this is new talk actually here. We are also studying binary orbital motion or flyby. And we want to study effect of flyby on the circumstellar disks and planet formation. So, L50 planet region, this is my favorite region. And I'm observing this region with ASIAA and ALMA with Paul. So in this region, there are three binaries. One is L50, this is binary image. And there are three binaries. One is L50 IS5. And second one is L50 NV. And the third one is XC here. So I will talk about all of these three sources. And first, these L50 IS5 and any protostars class 1 binaries. And Exeter is considered to be class 2 binaries. Yeah, so this is an image, VLA image of 50 IS5 and NE. And also Exeter. These are from very observation of these sources. So these are SMA and ALMA images of those three sources. So upper panel show SMA image of those binaries at gas continuum images at 0.9 millimeter. So with SMA, in the case of IS5, we usually just one block. In any, you could see some kind of structure, but not very clear yet. Exercise just we couldn't resolve two sources, but now we have ALMA. So with ALMA, these are ALMA images. And by the way, these five are in the same linear scale. This one is a zoom-in view. So both in IS5 and NE, we found some spiral-like structure, which is not seen here. But and also L50 and NE, you see this kind of two arms, including so-called N=1 mode. So the spiral arms are skewed towards the western part. Western part is much brighter than eastern part. And in Exeter, by the these are circumbinaries. these are circumstellar disks. But in the case of XCR, we don't see circumbinary disk in dust continuation, even with ALMA, but we see some kind of structure in two circumstellar disks. So I see this kind of view. So I will talk about this later. So let me show let's compare these two images. So I compare these two images at the same linear scale and also at the same brightness temperature scale. So what we see is that first the size of the circumstellar disk, circumbinary disk in L50 flare NE is larger than that of IS5. And also structures are different. In NE, as I told you, there's some with M equal 1 mode, which is not clear in IS5. IS5 is more like a clear two-arm spirals. But in IS5, the size of circumbinary disk is smaller, but the brightness temperature is much brighter than that in NE. So these are two differences. And we made numerical models to explain, to reproduce this spatial structure and also velocity structures. So this is one of Matsumoto-san's image to reproduce observation result of IS5. So we have two circumstellar disks, and from each circumstellar disk we have this arm structure. So, and also we made observation simulation, and we compared our observation and this model, and we found a nice match between observation and theory. But here I will talk about this part in between the two circumstellar disks, this connecting part. So gas motion inside the Hiragi in L51 S5. So this right panel shows our numerical simulation. So with two circumstellar disks, but there's some bridge feature here. Okay, and this L1, L2, L3, so-called Lagrangian point. So this left panel is the observational position velocity diagram, and middle panel is a position velocity diagram of our model. So in the other part, you see this structure. These are from circumstellar disk, circumbinary disk. But in between this part, around the L1 point, you see another gas component with some velocity gradient. So this component is also present in our model, so with velocity gradient. Even though the amount of velocity gradient is slightly different, but it is a similar gas component. And this gas component comes from actually this component. So I would say we found a splitting gas component around this L1. So bridging gas component around L1 is resolved. So I got my central next XCR. So from ALMA carbon data from 2015 to 2016, yes. So we found proper motion of XCR B with respect to XCR A. So XCR B is moving from toward southwest, right? So then we can also measure the velocity of this motion, and we can calculate the kinetic energy. So the relative velocity is something like this one. And then kinetic energy is, the lower limit of kinetic energy is 5 times 10 to 43 eV. Because this motion is only on the plane of the sky. So if you consider 3-dimensional velocity, this should be a lower limit. Then on the other hand, we can also measure the gravitational potential because we know the mass of these two sources. These are optically visible, so we can measure the scalar mass, and then you can simply use those masses and this separation to calculate the gravitational potential. But in this case, this separation is a projected separation. So again, we have to think about 3-dimensional separation. Then this number should be upper limit of the gravitational potential. Then, so this means this kinetic energy is probably larger than the gravitational potential. And this means this is not gravitational bound, but unbound flyby. So that is our recent discovery. We thought this is a normal bounded binary, but probably this is not a bounded binary, bound binary. Then we imaged newly available archival data of Exeter at 1.3 millimeter. So again, I already showed you this kind of possible like structure or tail. And this is a molecular line, newly available molecular line data of Exeter. So this white contour shows 1.3 millimeter continuum white contour. So this image is a 12 CO2 Duma moment zero map, and this one moment one map. So what is interesting here is that some kind of it's kind of Torrelles, or also how to say this kind of interesting structure with some velocity here, as well as the stretch component and pulsing component. And we have just started collaboration with Curiel and Jeremy Smallwood. So Jeremy made a nice flyby simulation of this particular source Exeter. So after this are some snapshot of his simulation. So here we could see some kind of this kind of built-in structure. So which could be related to this structure. Honestly, we haven't obtained a consistent picture of the observation and model, so we need more work. But anyway, we found this is a canonical flyby system, and data analysis of our data should be very important. And we also hope we can get another epoch of observations, new observations. So please give me ALMA time. We are trying, but we always fail. Great, this is so thank you. Thank you.
Any questions for?
Very nice talk. Quick question, if you go back to your energy argument, where you just were, but the energy argument, the kinetic versus the potential. What do you think the chances are that there's more mass around, like not just in the protostars, more mass in the area that might matter? And also, just to go with that, what if there had been more mass and that is now being liberated? In other words, not a flyby so much as an unbinding. Because in small clusters, we often talk about unbinding the cluster, because during the formation, material was actually pushed away. And so now you don't have enough for the kinetic.
So you mean basically no interaction? That's what you mean?
Yeah, well, no, not that they, but what if there's more mass in that environment that's helping bind them? Or what if there had been more mass and that mass is now lost and they now have been unbound?
Actually, we have molecular line data in this environment to show. I can prove that some. So we have many. So anyhow, we have some velocity channel maps of this region, and I don't think the mass is so big because the mass of the star is around 1 solar mass, compared to the stellar mass, the gas mass is negligible. Yeah, it's okay. Okay.
Thank you, Shigehisa. So now we can move on to the next talk. The next speaker is Salvador.
Okay. As Paul has told several times, I'm part of the Mexican-Spanish mafia. And since I'm part of the mafia, I can talk about whatever I want. So this has nothing to do with Paul, sorry Paul. This is something completely new that I'm doing. You know, when I came back to Mexico, it was 1995, and it was the year that the first exoplanet around the solar type star was found. So when I learned about that result and I read the paper, I thought to myself, I want to do that. I want to be a planet hunter. But of course, I was young, I was just hired in the Institute, so I didn't have the time to do it. So I had to wait. A few years ago, I decided that it was time to do it. It was now or never. So I started thinking how to search for exoplanets. And then, well, if you see there are many planets already found. More than 5,000 planets have been found and confirmed. And there are more than, close to 3,000 exoplanets found, not confirmed yet. So there are many planets already found. But if you see how these planets have been found, there are three main methods to find them. There is the transit, which is the most important one, radial velocity and direct imaging. And there is one just lying there with very few exoplanets. So I said, well, since Gaia was about to be put in orbit, I said, astrometry is the way to do it. Let's do something new, something different. So I decided to do astrometry. Now, how to do it? Well, astrometry is kind of a, it's something very old. So it's actually the first way that people looked for exoplanets and never gave good results. So, and it's also kind of boring because you have to observe many times, and every time you observe, the only thing that you get is one dot. Just the position of the star. So you have to collect many observations, many dots, and then you get something like this. Doesn't make sense, right? So you have to apply a model to try to get some sense of this. So you apply counter motions and parallax, and then you fit the dots, and you get a good fit. So that's perfect. We get the distance, we get several things. So we can remove the proper motions, and we get the parallax. We can remove the parallax, and we get the receivers. So These are the residuals. So the question is, do we have a planet here or not? So, actually the residuals are, even though they are very small, they are big compared to the precision of the observations. So there is something there. And I know that there are 2 planets orbiting this star because these are synthetic data I made. So I put the astrometrical signal of 2 Jupiter mass planets. So this is the kind of signal that we have to look for. We have to dig inside this to look for exoplanets. So what we're looking for is the astrometrical signal, which is basically this equation. So it depends on the mass of the star, the mass of the companion in general, and the distance of the companion to the center of mass. So this little thing here is the astrometrical signal, the thing that we're looking for. So we can see what to expect depending on the mass of the star, depending on the orbital period. So in this example, this is actually a theta star in Ophiuchus, half mass star. This is the mass of the companion, this is the orbital period. So you see, the only thing that we could find here is low mass stars, brown dwarfs, and it would be very, very hard to try to get a super planet. But it might be possible. This is the astrometrical signal that we would expect, each one of these curves. And this green curve here is the limit that we have with the BLBA. So that's it. That's what we can get. However, with low mass stars, this is different. So we will be able to find exoplanets of different masses. See, so in theory, it should be easy to find exoplanets around low mass stars. However, in practice, it's really, really difficult to do it. So I decided that looking for exoplanets using astrometry was not enough. I had to make it harder. And the way to make it harder is to do it in a way that nobody else has done it. So, using radio observations, not optical observations. So now I'm going to show you some of the results that we have obtained so far. Not many, but I think that each one of them is very important. This is a very low mass star. You see here the mass is between 60 and 80 Jupiter masses. So it's just at the limit between being brown dwarf and being star. And it's close by, nearly 11 parsecs away. So you have to get many observations to try to search for the astrometrical signal. So in this case, we did the fit of the proportional parallax, and we got these residuals. So can you see the trend here, the temporal trend? So when I saw this, I said, wow, there could be something there. So I included the fit of a Keplerian orbit, and then we got a better fit, so we got a signal. In fact, what we found is a Saturn-like planet orbiting this very low mass star in an orbit closer, more compact than Mercury in the solar system. So it's a very compact orbit and a very low mass companion. Another example, this was even more difficult because this is a binary. So we have to take into account the companion. So this is also very close by a star. The distance is 6 parsecs away, and they are very low mass stars also, and dwarfs. So we also had several observations with the BLBA, and since it's a binary, and it has been observed in the infrared, we included a relative astrometry obtaining the infrared and optical. So we were able to fit the orbit of the binary, the orbit of each one of the 2 stars, and also to search for possible exoplanets And so in this case, we found a two-mass Jupiter, two Jupiter masses, a companion, which is a planet, orbiting the main star. Okay? And the other thing that we found, which is also very interesting, at least for me, is that the orbits are not coplanar. You see, the orbit of the planet is almost perpendicular to the orbit of the binary system. So this is a very strange configuration. See, this is the first time that something like this has been found. So I'll show you that later on. Another source that we observed is a Theta star. So actually, I wanted to see if we were able to find something around a Theta star. So this is Dwarf 21. This is a weak-light Theta star. It's around 135 parsecs away, so it's an Ophiuchus. And we had also several observations with the VLBA. In this case, we detected two companions. One of them, we detected this first companion directly. So this is just the maps of the observations. And also with the astrometry, we detected a second companion. So we didn't detect it in the images. Because of that, we were able to find the mass of the star, the mass of each one of the companions. So we obtained that the mass of the companions is 35 and 44 Jupiter masses. So they are not really planets, they are brown dwarfs. But you see, this is a Theta star, very young Theta star, so these are very young brown dwarfs, right? Okay, let's still have a little bit of time. So this is another example. This is also a binary. So binaries, and this is something that I didn't know it was a binary. I discovered it was a binary. And we detected both stars. So in this case, this is also close by star, very low mass binary, 166 Jupiter masses for the binary. So in this case, we also obtain the orbit of each one of them. So even though it's a very close binary, I found some infrared observations, so relative astrometry of the two stars. So I combined that, and we obtained the fit of the binary for each one of them. So in this case, what we found is that the mass of the stars, one is 85 Jupiter masses, and the other one is 67 Jupiter masses. So one is a brown dwarf, and the other one is a very low mass star. So each one of them is different. So every time we observe a source, we get something completely different. So far, we have found 4 possible planets. Actually, you can see them in the catalogs, exoplanet catalogs. So this is a very small contribution so far, but this is something that can be done now. So these results prove that we can find exoplanets using radio astrometric observations. But in the future, we have other interferometers. So much better interferometers than the VLBA, right? So this is the timeline. So this is what we have now. So we have been able to find some exoplanets, and hopefully we'll find a few more. Then Gaia will come up. I mean, Gaia has been observed for several years, but the data will be released in a couple of years. So we'll be able to search for exoplanets using Gaia's data, using astronomy. And later on, probably with the scan and mainly with NGVLA, we'll be able to search for exoplanets. And I done some calculations just to see what kind of planet we would be able to observe with the NGVLA. On the left, this is Theta stars. See, you see 2 different distances, just to see the kind of planets we would be able to find. and this is low mass stars also at different distances. So in the case of Toroid stars, with the NGBLA, we'll be able to find Jupiter-like planets using astronomy. In the case of M-dwarfs, low mass stars, we'll be able to detect very easily Jupiter-like planets, but also Saturn, Neptune, Uranus kind of planets, and in some cases, even Earth-like planets. So this is something that I'm really looking forward to, and this is in about 10 years, so hopefully I'll be still working on that and probably be able to get the exoplanets. Okay? So, thank you very much. I leave it here.
Any questions?
There is one up there.
Yeah.
Oh,
Yeah, you can go ahead.
Salvador, this is really interesting. So you said you found one system that was an M dwarf, very tight orbit around an M dwarf. Is that right?
yeah, the last one? Oh.
Is it in the habit? So my question is, have you found anything in the habitable zone of its parent star? So is that system that you found that's in a tight orbit around an M dwarf, is that in the habitable zone around that M dwarf? Is it?
This one is just outside the water line,
Okay.
the indoor.
Yes.
In the case of the planets, they are way outside the habitable zone.
Okay.
So, you know, there is something very important about astrometry, and this is that it's more sensitive to planets far from the star.
Right.
The further out, the stronger the signal.
Understood. Okay.
So I don't expect to find planets in the habitable zone.
Okay. All right. Thank you.
Not with this.
Okay, one last question from Mike.
First of all, it's always nice to see people trying to detect exoplanets at radio wavelengths. My question is, so we know that M dwarfs and brown dwarfs are inherently variable as well. So how do you account for that variability when you're taking into account these high, let's say, microsecond or some maybe sub-millisecond position variability? So how do you account for the flux variability in the brown dwarfs as well? Do you take that into account while we are doing the astrometric measurements?
I'm sorry, I don't understand your question. Could you say that again?
Yeah, like M dwarfs and brown dwarfs at radio wavelength, the flux can be highly variable, like maybe order of magnitude. So do you take that into account when you're doing the astrometric fits? The variability of the M dwarfs?
What? Sorry, I don't understand what envelope you mean?
Like the radio emission from M dwarfs.
Oh, the emission, where the emission is coming from?
No, yeah, that is like a long open question, but the emission itself is variable. Like it changes over time. So do you account for that when you're fitting for this?
The time variation of the source?
Yes.
Okay. Well, I mean, the time variation is very important because you detect or you don't detect the source. But we have checked that when there are, some of these sources have flares, right? So we have made maps of during the flare and inside the flare just to be sure that the position that we measure is that of the star, not something that could come out from the star, for instance. So we take care of that because it could be possible that maybe there are some flares and then the position just shift a little bit.
Okay, thank you very much. Yeah. So let's move on to the next talk. So our next speaker is José María.
Thank you.
There's 2 minutes left.
Good afternoon. During these days, these fantastic days of this meeting, I have heard many times the phrase of the Mexican, Spanish mafia. So, well, I have to recognize that I'm a little bit nervous. To talk in front of the Godfather. So, well, I will try to do my best in this talk, just in case. So, what this talk is based on ALMA observations and made by this team with José Francisco Gómez, that in particular sent to you our meeting from Granada. You know that he was working with you for 2 years. He learned many things with you. And they are also good friends, José Miguel Girard, Jorge Cantó, Guillem Anglada, Protolist online, Salvador, Curiel, and other very good friends. So well, I divided my talk in these 3 parts. First, to summarize the main observations to follow the evolution over 20 years of the VLA2 wide laser cell, then to present the ALMA observations, in particular continuum for María and SIO, and to make the conclusions that I anticipate that the conclusions are the title of my talk. Okay, no, sorry. Let me keep. Okay, so the W75 star-forming region is a massive star-forming region located at 1.3 kiloparsec, and it has a very extended bipolar molecular flow seen in CO, extended over several parsecs of length, and there are many indications of massive star formation with radiocontinuum emission, water lasers, methanol, OS method, etc. At the center of this region, there are 3 massive protostar, VLA1, VLA2, VLA3, traced by the radiocontinuum emission at 1.3 billion. This is thermal free emission from ionized gas of massive protostar. The work was done by all these authors, including José Francisco, Luis Felipe Rodríguez, Paul, Salvador Curiel, and Roberto Vázquez, also from Mexico. The most interesting thing that we found in the late of the 90s was when we observed this region in water lasers using the VLA and the VLBA. So, and also the continuum emission. So in color is the continuum emission of VLA1 tracing a radio jet elongated in this direction. Here is around VLA2 is a compact continuum source, and each symbol of these are the position of different water lasers. So the most important results here were to see first the stark contrast in outflow geometry in 2 sources located very close between them. In the case of VLA1, the masses are orientated and located along the major axis of the radio jet. However, in this case, are surrounded the compact continuum source. Using proper motions studies during several epochs, we found the proper motions of the water masses, so they are moving in this case in VLA1 in this direction. However, in this case, the masses traces an almost isotropic outflow expanding in multiple directions. It was very surprising because, well, you know that according to the correlation model, we expect already at the beginning of the evolution of the protostars collimated outflows. But we don't expect, or we don't know how to produce isotropic outflows at the very beginning. So what this brings 2 important questions is to know what is the origin And what is the evolution? Well, I anticipate that we don't have the answer about the origin of this kind of outflows, but we know about the evolution. So during more than 20 years, we have observed this major cell. This represents the elliptical fields to the one major cell during different epochs between 1996 in red, green is 2007, 2012, and you see that at the beginning of our observation is almost a circle shell, and in 2005 it increases, but also keeping more or less a circle, and in 2007 it increases, but being more elliptical, and at the end in 2012 more elliptical. We estimated that the expansion velocity is 30 kilometers per second. More recently, using the European BLBI network, also in different epochs, we see the shell in contours is the radio jet. Perhaps the most interesting thing here in these observations were to see that these masses are stopped, are halted for something that we don't know. We proposed in the work by Gabriel Surfis and collaborators, we proposed that here there is some kind of obstacle halting the expanding motions toward this direction. Also very interesting was that we found first the masses are evolving, are changing the morphology, being more collimated with time, but also the continuum. The continuum emission in 1996 was a compact source, and in 2014, so almost 20 years after that, we see this elongated structure, and the spectral energy distribution is consistent with a radio jet. So, well, as I said before, here we propose that there is some kind of obstacle that is impeding the motions. Okay. So, to interpret this, we suggested, we proposed that what we are observing in this kind of objects are episodic, short-lived, tens of years, because we see the evolution in 20 years, and initially isotropic. And we proposed that there is a toroidal density distribution, that if you have at the beginning an isotropic outflow evolving in this toroidal density, at the end you get a collimated shell. So doing the model, we obtained these parameters that are very reasonable, and we thought that the beginning of the expanding motions of this shell was in 1984 and 1985. Okay. So this region has also, previous to our observations, SMA observations, and the SMA, the work was by me and collaborators. There are 3 millimeter cores, and the main core is around the 3 massive protostars. So we observed this with ALMA, in continuum, formaldehyde, SIO, and maybe other lines. And as you see, the ALMA observations resolve the individual millimeter cores observed with the SMA in multiple millimeter cores. This is not surprising, because we have better resolution, we have better sensitivity, even that the source is at 42 degrees of declination, but it's nice. And the 3 massive protostars coincide, has also counterpart of millimeter emission. However, the most interesting thing, if I can, okay, yes, are the molecular lines. This is the integrated emission of the formaldehyde and the position BLA1, BLA2, BLA3, but we find, well, with these 5 pointed studies, the position of the halted measures that we found with the European BNBI network. As you see, there are several plans, but none of them coinciding with any of the massive protostars. So, well, because the position of these of the halted measures, we identified this cloud as the obstacle predicted by our paper resources and collaborators to halt the expanding motions, and just making a very simple estimation, a thermal round pressure between the wind and the gas, we obtain densities of 10 to higher than 10 to the 7 particles per cubic centimeter. That is reasonable. More interesting results, the most important result is when we see the integrated emission in SIO is completely different than the formaldehyde. The SIO is well concentrated and mostly on BLA2. And BLA1 and BLA3 do not have enough SIO emission. This is a zoom of the region, and you see what we resolve it when the emission is very well centered on BLA2. It's elongated the structure, well resolved. The fact that we are observing SIO concentrated on BLA2, this indicates that they are very strong shocks around BLA2. Well, this is the major excess of the SIO structure, and this is the orientation of the expanding shell that we observe in one emissions. And you see that the elongated structure is almost perpendicular to the major excess of the expanding motions of the one emissions. The structure has these sizes, about 1000 AU in the major excess, and because this distribution, we interpret the SIO structure as the toroidal structure previously theorized by our previous work to explain the outflow evolution. And with respect to the kinematics, also is very interesting. This is a position velocity diagram along the major axis of the elongated SIO structure. And the most interesting thing comes from these two components at very high velocities, very high blue shifted velocities at both sides of the main emission of the SIO, making integrated maps in the red bar and the blue bar. What we found is this: when in blue are the blue shifted high velocity emission, in red the red, and you see that the high velocity components are surrounding BLA2. It's not centered. So this means that they are tracing a wide angle outflow around BLA2. And this is again the position of the halted star. We see, or we suggest, that there is also a possible velocity gradient in the core of the SIO with a velocity gradient of 6 km per second. And if this is true, this could be gravitational bound by a central mass of 10 solar masses that is consistent with the mass of the massive star. And these are the conclusions. So the most important one is that we think that the data consisted with an asymptotic with a white outflow in BLA2. Thank you.
Thank you.
Very nice stuff. I'm just wondering, in the larger scale, you have this with more east-west outflow. Is that associated with VOA2 as well, or
You say the east-west outflow, where?
in your introductory slide, I thought there's some large-scale outflow.
No, you say here.
Second, maybe your second slide, maybe third slide.
In the second slide at the beginning.
Yeah,
Yeah.
that one, yeah. So that's,
Okay, you see, okay.
that is much larger scale, I guess, right?
We didn't take attention for that. You see this.
There's a seal redshifted, right, to the bottom right.
Yes.
And then you have roof. Is that,
We have analyzed this kind of thing.
that's a seal 2-to-1, I believe, or 1-to-0 that Deborah Shepard published.
Yes, well, with our ALMA data, we have these lines, and this is the next work to analyze. But you know that there are many lines. What is the CO, and even the SIO, a more extended region. We have concentrated just at the center of the region, so I did not pay attention about this feature.
And on your first slide, is it Jose Francisco's at the beach instead of coming here?
Yes, in Granada. But I have to say that he's now in a committee to decide for permanent position, so he cannot attend to the meeting, unfortunately.
So Jim, is there a mass estimate for the SIO Toroid?
Well, because we only have one line, we estimated the mass of the Toroid, just taking the critical mass to excite the SIO.
Density.
So it's higher than 10 to minus 2. So it's not so massive. No.
Right. So the question I'm asking is, if you have the outflow expanding and possibly pushing that, whether 0.02 solar mass is enough or not, in terms of
Yeah.
the energetics and the momentum.
Yeah.
Okay.
Okay, thank you very much. So that's the first part of this session. So before you enjoy your afternoon break, we would like to have a group photo. So please move outside. Outside building. Okay, yeah. So please move outside on the stairs, and then please come.
But before starting with science, Satoshi has some announcement to make.
So this is LLC announcement from Satoshi, me, which is only one topic. That yesterday I put this travel guide. This website, and this is travel guide. And there's a new topic, number 2, craft beer bars. It's only around 30 minutes from here or Howard Hotel, and there's a link to the map, PDF file, and you can find all the, my highly biased toward me, my preference about the craft beer bars, sorry? Well, I said it's my preference, so if you don't like my preference, maybe not, but yeah, it's also 30 minutes, within 30 minutes surrounding, and so if you need nightlife, go ahead. That's it.
Okay, so we will start this afternoon session with after coffee session. So please, I would like to ask all the speakers of this session to come and just set up their presentation once we are in the question session of the previous speaker, because we have many talks. Okay. So the first speaker of this after coffee break will be Guillem Anglada, and he will be talking on the SBS 13 cross proto-binary system.
Hear me?
Yes.
Good afternoon from Granada. I am Guillem Anglada. I am the next one in the Mexican-Spanish gang. For not being here in person with all the friends of Paul, but I thank the organizers to allow me to participate online. I will share my screen and I will summarize the results of the last paper we published in collaboration with Paul. ASIAA-13 is a star which is the assumed driving source of the well-known orbital object system 711 in the NGC 1333 star-forming region. This star was discovered as a near-infrared source, and around 1990 it becomes optically visible in Captain Course and has been visible since then. On the other hand, this star is a strong millimeter source, so it's like a contradiction that it's both a visible star, suggesting that it's relatively evolved, the youngest stellar object, but at the same time it's a strong millimeter source that suggests that it is a class 0 or a very young protostar. In 2000 we discovered that in radio this star was actually a binary with separation of about 90 astronomical units, and we proposed that one of the stars was the optically visible one and the other one was much more embedded. Later we observed with the VLA, we found that the eastern star, VLA-4b, was strong at 7 millimeters, suggesting it was associated with the disk of dust, and the other one was much weaker. So we suggested that the A component was the visible star, and the other one was the more embedded one surrounded with circumstellar disk. We have been, do you see? Okay. The formation of one or two disks in a binary system depends essentially on the specific angular momentum. So if the angular momentum is low, then one circumstellar disk is formed around the primary. As the angular momentum increases, then both in the primary and in the secondary star are formed circumstellar disks. And if the specific angular momentum is still higher, then it starts to form a circumbinary disk surrounding both protostars. So it depends on essentially on these parameters. To further study this, we undertake for several years VLA observations and ALMA observations in order to decipher the 3D geometry of the system, to estimate the temperature densities and all physical parameters. And I will present a summary of the results obtained by analyzing these observations. And we try to calculate everything in a self-consistent way. So we did not make assumptions on the mass of the stars or anything else. We derived everything from the observation, and we just assumed the gas to dust mass ratio and the dust opacity. And we were able to obtain these parameters and the chemical properties on a scale of around 20 astronomical units. Again, observed the binary. We obtained data at several wavelengths, and with the improved position of the star, we realized that actually the optical component was associated with the eastern component, with the B component, rather than with the A component. We also found that there is a slight separation between the radio and the optical position, and we think this is real, and probably because there is a jet which is well detected in Iron 2 by Coda Pancini, and this jet probably created a cavity, and what is seen at optical wavelengths is not directly the light from the star, but probably light scattered in the walls of this cavity, explaining this displacement that had been observed in another object. We suggest that until 7 millimeters at longer wavelength, we are seeing free emission here in this improved image with the Bay configuration data. We can see that the station of the radio jet, and at millimeter wavelength, at 7 millimeters, we see that this is mainly elongated perpendicularly, and probably at 9 millimeters we see a combination of both things. With the ALMA data at 0.9 millimeters, we realized that actually both components are associated with dust, and removing the extended emission, which traces several, at least 2 spiral arms, maybe a third one, we see that these have sizes of the order of radius of the order of 10 astronomical units. Also, from the brightness temperature, we obtain lower limits to the temperature. And we found very high temperatures of the order of several hundred K. It is worth noting that this is also found, this kind of high temperature were predicted in a detailed modeling of the L5051 IRS-5 by Osorio et al., and later confirmed by the ALMA observation of Takakuwa that have been presented before. Another interesting thing is that the shape of the spiral arm show that the rotation of the system, as observed from Earth, is counterclockwise. From the molecular ALMA line, we obtain what we think is the circumbinary disk. We see that there are differences in the intensity and the line width across this circumbinary disk. We found many molecular lines, and we know that the emission is much weaker towards the eastern component. But we think this is because of the very high dust opacity that makes that when we subtract the continuum, the molecular emission also decreases, because the optically thick emission, the both emission do not touch, so the subtraction is not perfect. What is interesting also is to see the kinematic from the line of sight velocity. We see that there is a clear velocity gradient across the circumbinary disk, and this gradient has a yin-yang shape that we interpret as a combination of infalling and rotation of the gas. And we see that the direction of the rotation inferred from this of the molecular emission also is counterclockwise, in agreement with what suggested by the spiral arcs of the continuum. Another very interesting thing is that we detect ethylene glycol only towards the A component, and this shows a clear velocity gradient that we think is produced by the circumstellar beam. So we also, from several transitions of the same molecules, we are able to determine the rotational temperature of the circumbinary disk. We see that this is rather uniform, of the order of 140 K across the disk. This is a relatively high temperature, and we also see differences in the abundances. So another interesting thing is that mainly from the DLA observations, we are able to study the proper motions of the system along 25 years. So we see that the B component gets closer in declination to the A component, implying that, again, a counterclockwise motion. From this we can obtain the 3D velocity of the relative velocity of the system, because we have the line of sight and the plane of the sky motion. So we can derive the total mass of the system, that is one solar masses, with a period of 850 years. From the study of the gradient toward the A component, we derive the mass of this star, that is 0.3 solar masses, and from the large scale velocities, we see that there is an acceleration that we model very well with masses of 0.3, 0.6, that is in very good agreement with the total mass derived from the proper motions. From the DAX, we can calculate the mass of the circumstellar disk from the 7 millimeter data and from the 0.9 millimeter data, and with time masses of several Jupiter masses. The range of masses, because we found that the temperature in the disk is of the order of 140 K in the outer part, but much higher towards the center, so we calculate both masses. And finally, we can estimate the specific angular momentum of the system for each component, and we see that to form a circumbinary disk, we need this critical specific angular momentum of around 0.1 from 0.8. We see that our data is of this order, and so we expect that, as observed, two circumstellar disks and one circumbinary disk are formed. Here I show a gallery of systems that have been observed with similar detail, and this is the full list of physical parameters we have obtained from the masses, the sound of speed, and other parameters, and I think SES-13 is an excellent test bed for numerical simulation of the earliest stages of binary formation. Thank you.
Thank you, Guillem. Questions for Guillem? No? Yeah, Narioshi.
Thank you for that very interesting talk. So I'm just curious about the you said you are talking about the Indian shape. Which slide? I took a picture. So one of my slide you are talking info motion. You said Indian shape.
I am sorry, I cannot hear the sound well.
Oh, okay.
My take.
So let's see. My voice doesn't go through the.
Nakayoshi has a question about the, where's the microphone?
The
linear
yin-yang shape.
Oh, the yin-yang shape, the one with a velocity gradient, a redshift and bullshift. This one.
Yes.
Yes.
Yes. Thank you. Now it's better. Sorry. There is a rotation. Can you see my figure?
Yeah. Yes.
If there is a rotation, we expect a velocity where one side is blue shifted and the other one is red shifted. It means that the eastern side is moving away from us, and the side is moving up.
Okay.
However, if you in addition you have in-fold motions, then you will have that in the northeast side, the velocities will be more redshifted than in the southwest side. So this makes this distortion in the velocity field. So the separation between the red one and the blue one is not like a straight line, but is twisted in this way, making this of yin-yang shape.
Yeah. So that name comes from in Chinese. I'm just curious if there's any difference. I want to just know it.
So I could not hear the comment.
It's okay. I can follow up.
Any more questions for Guillem? If not, let's thank Guillem again. So our next speaker will be Luis Zapata, and he will talk about violent cosmic explosions in massive ion clusters.
Maybe should I?
往右边，然后从右边往上。play.
And the microphone is okay. Thank you.
Well, okay. Well, let me start because the time really goes. I'm going to talk something that I actually started to work with Paul at some point, but I was at that time I was at CPA, I was in the MPI, and we started to really do a really large mosaic in Orion, and we started to work more in Orion Cairo. That is a different region that I show you. Let me talk a little bit about this impressive image from Chinfei Li, Hirano, Aina Palau, and all the people from Asia. This is the electric object 211. You can see here from the SMA. It looks really fantastic. It's a really collimated outflow from the ASIAA, and even the CO also looks really fantastic. This outflow. In the gray scales, you can see the H2. That is those kind of shocks on the final. The Protostar that is really in the middle of this outflow is powering this kind of really fantastic and collimated outflows. This is our picture of the outflows and all these things. The main idea is that you have a Protostar that is really accumulating mass and is trying to grow and grow and grow in mass, and the thing is that mass needs to really lose the angular momentum, and you have this kind of things that really now understand a little bit more. If we go and try to do some PV diagrams that we can see the kinematics of the outflow, you can see from here, this is from the CO emission, again from the SMA, you go to the PV diagram, here is the velocity, rocket velocity versus the projected distance. You have a bulk of molecular emission. The dots here are the dots that are coming from the cubes. I mean, every cube, when you see condensation, you can extract the position and the velocity, and you can plot it here. Something that is really nice, that you started to see this kind of really lines in the position of the dots. More or less, this is something that is the internal working surfaces that Canton Rada already displayed. And you can see many of them are associated with shocks, internal shocks in the outflows. And this is something that in many outflows we can see this kind of structure. We don't see really clear this kind of whole outflow, but maybe in some ones are more clear. Something that came at some point was this kind of explosive outflow that we started to work. This is a really nice picture from the Orion Nebula. You can see Orion Sur that I already talked yesterday about this region.
Well, now we're working in this kind of, northern region, and the name was Kagoshima. This is a survivor image from the infrared. That means that you're really seeing the shocks. And this outflow was really impressive from many years ago. And the idea is that we started to do it with SMA. We put the proposal and we started to observe mostly CO, 13CO, C18O, and all these kind of lines to really try to see the kinematics of this outflow in Kagoshima. This is what really we found. You probably know about this. It is the paper that I actually put in 2009 with Paul is here. We actually collaborated on this team. Here is the result from the SMA. You can see the CO in blue color and red color, that is redshifted and redshifted emission. There are many filaments in the different directions. If you do the same experiment, you plot this kind of filaments in the PV diagram. You can see the projected distance, and here is the radial velocity. This is something fantastic because every filament seems to point to a single position. That means there is some kind of origin that is more or less here, and in velocity there is also some kind of origin that is really like explosion at some point. More or less the age of this explosion occurs over something like 700 years ago, more or less is the time that occurred this thing. But the nice thing is that this outflow turns to be something really different. This is not the typical outflow, this is another thing, and it's more associated with explosion. And this is the key thing that we started to think. After this, we started also to push observations with ALMA and try to be more sensitive and try to see the monostructure of this outflow. It is more or less the result. This is the CO emission from ALMA. You can see that this is a really fantastic thing that happened there in Orion. You have like 100 filaments in different directions. You see that the explosion is really symmetric. I mean, it's filaments in all the directions. And you can, of course, go and try to see the 3D dimension. And in the 3D dimension, it looks also really fantastic. I mean, you can see in the middle is the cloud velocity, and if you go away from this cloud velocity, you see higher velocities, and you see the filaments pointing to a single position. And that was also a really nice thing. I mean, we have this kind of new outflow with many filaments in different directions, and this is probably related with some kind of stars that are really moving again also in a different directions. This is a movie that the people in ALMA made for putting the CO data on the cube, and then put the H2 emission, and then the CO moving one in this beautiful video of the explosion. You can see it again. What really looks like. You even really have music for this thing. Much better. And the main idea now is trying to explain this outflow. Now, what really happened here, and what really think about what really produced this outflow. In the middle of this outflow, there is some kind of, rumanoid stars. I know maybe you know the star that is so size of N, Pn. Those sources have really large proper motions, like something like 22 kilometers per second. The kinematical age, where those sources supposed to be really close together, is something like this, and the age is something like 500 years. This work was made by Rodriguez, and all these, filaments that I saw in the SMA and ALMA points toward this, position. Something is related with the star start to move, the explosion occurs, and all these things seems to be on the same thing. If you go and see more recent data, there seems to be that you have more stars moving from this position that is more complicated to explain what really happened here. This is the main idea. Another thing is we started to find more explosive outflow in more regions. That's really a surprise to us. We started again to observe this G.89, that is a really fantastic H2 region. Paul Ho and many people from CPA and ASIAA already work with this source. And the idea is I started to really measure again the CO emission from this source. You can see from here the image from the VLA, the SMA, there's some kind of ring. If you go to the infrared, you also find some kind of, cloud that is kind of ring structure. There is a really massive star that is associated with a failed star that is some kind of all-time star that is really bright. And something had to do again with the clusters of massive stars. We did observation with the VLA, and again we found another case that we have explosive outflow associated with this region. Here is the CO emission. You again see the filaments pointing in the same position, that is something in the center of this H2 region. If you do the same experiment, the PV diagram, you find really similar that we already found in Orion. And this is another really impressive result that we have a second case for the explosion occurring in a massive star-forming region, and it is something really similar that is really happening in Orion. This is give you some idea that this phenomenon is really happening in this kind of forming star formation region. And here is again some kind of the 3D structure for this outflow explosion. You can see the whole rows of every filament from this. You see that if you go away, there's going to be really blue ones. If you go really close to the center, to be something that are really green colors. That means something like a hole of flows in every filament. And then is another case that I already actually discovered. The name of this source is IRAS 12336. And again, we found the same structure that in the other two cases in the Orion KL in G589. And now in this source, you see there is again the blue and red color of the CO. The contours here is the dose emission, that is some kind of ring structure. And in the center of the explosion seems to be here. And so many of these filaments seems to point in the same direction as Orion. And the idea now that we want to explain about this is that we have two problems now. One is, what is the rate of explosive outflows in the galaxy? This is one of the questions that we want to start to answer. And the other thing is the nature of the explosive outflows. What are really producing these kind of explosions in these high mass star-forming regions? We have two questions here. The first question that we started to really think is, we started to see where are all the explosive outflows in the galaxy. We can start to estimate what are the rate, more or less, from these outflows and the distance and the ages that we have. And more or less, the rate that we started to find is something that once every 100 years more or less in the galaxy. So this is really close to the supernova ray galaxy, more or less, if we do good counts. And this is also really similar to the formation rate of the massive stars. I mean, you can go and estimate these numbers. This is more or less 1 in 50 years, more or less is the thing that we are thinking. And this is really important because look like 1 or 2 massive stars are forming with explosive outflows. That means it's maybe related with some common merge or something like that. The other thing is try to explain a little bit more the nature. The nature is really difficult question because we really don't know the physical mechanisms to produce all the explosions. I mean, in the explosion you see some kind of really compact bullets in many directions, and what really power these bullets to go away is no easy problem to explain. Something that we are working with Jorge in Mexico and other collaborators is if you have some kind of cluster of really chunks of material and then you pass some really compact object in the cluster, then you can have this kind of motion like a Hubble flows. And this is the idea that we are now thinking how to explain this explosive outburst. And I am going to stop here. I'm going to leave you like that with this picture, and thank you.
Thank you, Luis. Thank you for being time. So, questions for Luis?
Yeah, thank you for the exciting result. And I was just wondering if those, the luminosity of those exposed stars are brighter than the other stars. Luminosity the same, but you still see the
Yes, the luminosity, for example, for the regions, if you go to Orion Caelis, 10 to the 5 solar luminosities. If you go to the G5.8, it's around 10 to the 5 solar luminosities. Are really bright and are associated with a cluster of massive stars. I mean, you look like if you have some kind of really young cluster, you have probably this kind of explosive outflows.
Thank you.
Chillo?
So Luis, this is fantastic stuff, especially Orion. So I have a question on G5.89 because there's a strong H2 region already developed, right? So you see in the continuum, you already see in the shell. So how that affects the morphology and your interpretation? Could that be still consistent with a few outflows? Just like
actually, the H2 region, I mean, there is some observation from the recombination lines, and you have the radial velocity of the expansion of the H2 region, and that expansion really coincides with the age of the explosion. I mean, it's something around 1,000 years, more or less. That means that the H2 region maybe is associated with the remnant of the explosion that is moving the material away, and is creating also this kind of H2 region. In Orion, maybe you don't find the H2 region, but you have also some kind of bubble or something molecular shell that is surrounding again the center of the explosion. That is again that's related with the explosion. Also, if you look the stars, I mean, you look PN, SOSI, and BN, more or less that the velocities, the radial velocities coincide really well with the expansion of the gas, like 15 kilometers. And it's really similar if you go and see the furthest star is on the edge of the H2 region. That means that maybe it's related, that furthest star, also with the explosion. This is the idea.
We can discuss later because the energy budget may not work out.
Maybe.
So, quick question.
So, is there anything more in the fact that this filaments or this stuff that's shooting out is also breaking up in like regular segments.
I don't understand.
It's not a straight line. There is like segments, no? And they seem to be equally spaced.
I think
just by eye.
Maybe I'm part of the filaments that are breaking out when the proton is moving, and maybe it's related with this.
But it's not the same like the jets that show this more is probably episodic events, not each other forward. So this seems to be something different. If it's one, it's a signal explosion.
Yeah, I mean, if you have some kind of a bullet that is really traveling in the cloud, this bullet is breaking out because it's really like shocking with the gas, and then part of this bullet are really like living in different positions, and maybe are creating different filaments in different positions. That is the idea.
Okay, I think you can keep discussing the coffee break. So let's thank Luis again.
Thank you.
So our next speaker is Jesús Alejandro López-vázquez, and he will talk about multiple shells driven by these with ALMA observations in the ICE-CSIC and Outflow.
Okay, good afternoon. Today I am talking about a recent paper of the ALMA observation associated with the molecular outflow of HH30. So HH30 is a very typical protostellar object. Why very typical? Because you can observe a bipolar protostellar jet, and also you can see an accretion disk, but it's not a typical protostellar object because only you can detect a monopolar molecular outflow. If we analyze the ALMA observations, I would like to present the disk emission associated with the TCO, when you can observe that the accretion disk present the blue shifted velocities and red shifted velocity, and if we did the position velocity diagram, you can observe that the accretion disk present a capillary profile. If we measure the mass of the enclosed mass, is 0.45 solar masses. This value is consistent with the previously reported. If we focus on the CO emission, you can see the molecular outflow is extended until 19 arc seconds, and the black dots correspond to the nodes of the protostellar jet, and this is a SIO nodes. And if we analyze the velocity map, you can observe that the very close to the accretion disk, the molecular outflow presents the difference between the difference velocity. This difference could be interpreted like a rotation velocity in the protostellar outflow, and this part could be present an excess of the velocity and could be associated with the train material. And finally, the dispersion velocity map traces that the dispersion velocity is dominated by the accretion, by the protostellar jet. If we analyze the emission of the molecular outflow for the high velocities, you can observe that the high velocities traces the part very close to the accretion disk, and also traces the material probably associated with the train material. While the low velocity map presents a cavity. This cavity is a signature, is an evidence that the molecular outflow is hollow. And if we did the position velocity diagram along the jet axis, you can observe that the position velocity diagram presents a convex spur structure. This structure is associated with the molecular outflow driven by jets. So also in this region between 3 and 5 arc seconds, you can observe like an internal structure, like a multiple shot structure. These structures are detected by Lobet in 2018, and they found two possible shots in this molecular outflow. This structure is observed in the different molecular outflow like a HH4647 and DO Tau. And in order to find the different or the multiple shells in the molecular outflow, we made a cut in the position velocity diagrams perpendicular to the jet axis. With the position velocity diagrams, also we made a different cuts, vertical cuts, and obtained the different spectra. And the spectra, you can observe the multiple peaks in the mission, and for example, the inner peaks are associated with one shell, the medium peaks for the other shell, and finally the external peaks traces the other shell. If we analyze, for example, the molecular emission very close to the accretion disk, only see a one nested shell. While the medium heights, you can observe until two different shells, and finally for a very high heights, you can observe until three different shells. The two internal shells and one external shell. In order to obtain the physical properties, we can use the Lobet model too, and this model correlates the physical properties of these shells, like a cylindrical radius, rotation velocity, and expansion velocity, with the properties of a disk, of ellipses, like a minor and major axis, the center, and the position angle. If we correlated this model with our position velocity diagrams, we obtain the cylindrical radius, and the cylindrical radius in this plot, we have the cylindrical radius as a function of the height, and obtain that there is a power law. The cylindrical radius follow a power law of the height. Also the expansion velocity. The expansion velocity is in the line of sight, and this expansion velocity tends to a constant value around the 6 kilometers per second in the two external shells, and around 4 kilometers per second for the internal shell. And finally, the rotation velocity decreases with the height. We compare our estimation of the cylindrical radius with an emission of that very specific channel map. We can observe that the inner shell traces the wall of the molecular outflow, while the medium shell and the external shell only detected in a heights around between 0 and 5 arc seconds. This effect could be associated with the cooling effects of the molecule of the CO line. In this zoom, you can observe with more detail that the internal shell, the medium shell, and finally the external shell. With these properties, like rotation velocity, expansion velocity, and specific molecular outflow, we obtain the launching radius, and you can see that the launching region is the same of the two shells. So, given that the region is the same, because we cannot resolve the accretion disk, we assume that the different shells are associated with the multiple ejection events. And with this assumption, you can measure the dynamical age, and with this dynamical age, obtain that the external shell, or shell 1, presented the age around the 500 years, while the medium shell is around 300, and finally the inner shell is around 250 years. If we compare with the nodes presented by ASIAA in the jet, we can obtain that the shell 2 is different than the A4 node. However, the shell 3, the more internal shell, is consistent with the node A3B. So this shell could be a result of a node and the node driving the node driven by the shell, by the wind, sorry. And finally, if we estimate the magnetic lever arm, we can obtain that this value is between 1.6 and 1.7, and this solution and the launching radius is consistent with the Anderson relation, is an indicator that these wings of these shells could be could be originated by the cold magnetohydrodynamic disk winds from weakly magnetized disk. And finally, the parameters like mass of the outflow, the mass loss rate, and the angular and linear momentum rate are consistent that these shells are originated in the accretion disk and also are producing at the different times. And this is the summary, and thank you very much.
Thank you very much, Jesús. We have time for questions, so please raise your hand. Question for Jesús? So I have a question in the meanwhile. So is this sort of onion-like outflow, the way that you should expect for all these low mass objects, right? Because you see these knots everywhere, or only the ones that you see some sort of precession?
Yes, could be an onion structure. However, we cannot detect the different molecules. Could be the inner region. For example, this could be associated or could be observed at different atomic lines or different atomic emission, but are not detected. Only detected the jet, and the jet is very collimated in comparison with the width of the shell, the internal shell.
So is this HS30 the only one that you know that has this structure?
Yes, exactly.
Any other question? No? So please extend Jesús again. Okay, so our next speaker will be Shigehisa, and he will talk about multiple outflows around the single protostar islands 15, 3, 9, 8, 3, 3, 5, 9. Okay.
Hi everyone, my name is Shigehisa. I'm a postdoc in the AGA. So today I would like to discuss multiple outflows on single protostar IRS 15398 that are found from a previous observation and our new observations. So as many of you guys know, planets form in protostellar disks. So understanding the disk formation process is important to understand the diversity of protostellar disks and eventually the diversity of planets forming inside protostellar disks. So in a classical picture, disk formation, the initial condition for this formation process is simple. So there is a rotating dense core and there is a magnetic field aligned with the rotational axis of dense core. But today we know that the initial condition for this formation process could be more complicated. So the rotational axis of dense core doesn't have to be aligned with magnetic field, and the dense core may not be rotating just the gust motion inside dense core could be just turbulent. So observation in this suggests this situation could are much more common than classical picture. So like misalignment or So misalignment between magnetic field and outflow are kind of typical. So just perfect alignment is much more rare, and also line observations of dense core shows much more complex velocity field, and that could be consistent with turbulence scenario. So the understanding the dynamical role of this initial condition is in this formation process is important. So class 0 protostar IRS 15398 is an interesting object and very unique. So this object has very compact disk like so like this is the high angular resolution, latest high angular resolution observation in dust continent with ALMA. So this structure, so the disk size is in dust less than 10 AU. And the protostar mass is estimated to be like 0.02 to 0.1 around solar mass, so this is quite low mass protostar. And this shows H2CO line emission taken by ALMA in previous work, and we can see clear primary outflow on this direction. And interestingly, previous work suggests that there is one more outflow which is perpendicular to the primary outflow. So this is primary outflow, and there is a weak emission here. And this component shows a velocity much higher than the infalling velocity expected from this protostellar mass. And also this component shows so-called Hubble-like velocity profile. So that is why previous work suggests that this is an outflow. And one more important point is that even observation at high angle resolution at less than 10 AU, this protostar looks like a single source. So around a single low mass protostar, the initial condition like misalignment or turbulence of dense core could explain these highly misaligned multiple outflows. So I will come back to this point in discussion later in this talk. But anyway, we have conducted observations using ASIAA Binaries to cover much wider area than the field of view of ALMA single pointing to investigate large-scale gas timeline. So the initial objective of our observation was to investigate like a core motion, but we accidentally found the third outflow in this system in field CO2 line. So in this talk, I'd like to talk about that. Right, so here's the observational results. So to do field CO2 line emission, color now shows those distribution. So we see many elongated structures, and looking at the center, there is a clear elongated emission in this direction, clear velocity gradient, and there is one more component. So this corresponds to the primary and the secondary outflows that are already reported in previous work. But outside of this ALMA single pointing field of view, we still see many emissions, and especially two of these structures appears very symmetric with respect to the protostar position, and those is also very symmetric with respect to the systemic velocity of this protostar. So it looks very like an outflow. So here's the structures of these two components. So these are position loss diagram along these two emissions. So here's just unresolved primary outflow component, but here's the velocity structure of two components. I said, and we can now clearly see that these emissions shows so-called Hubble-like velocity profile. So velocity increases with increasing spatial offset from protostar. So this structure would be pale outflow. And one more important point is that all these primary and secondary and these new outflows are highly misaligned. So here's comparison of dynamical time to figure out what we are actually looking at in this observation. So previous work suggests this kind of dynamical time scale for primary and secondary outflow, and we also calculated the dynamic time scale for third outflow based on the length and the maximum velocity. So especially between primary and third outflow, dynamical time scale is different by an order of magnitude. So we are likely looking at the time variation of molecular output direction. So what kind of physics could explain this situation? So outflow is ejected along the disk normal direction. So in this formation process, if this orientation changes, then outflow direction should also change. And this could happen if the angular momentum vector of infalling material is not distributed uniformly in space or time. And this could not happen in classical picture, but in this kind of situation, this can happen. So for example, in misalignment case, the specific angular momentum is more efficiently extracted in some particular direction, so it makes change in the angular momentum vector of infalling material. And turbulence case is much more simple, just the angular momentum vector are kind of randomly distributed, so this orientation could change in the disk formation process. So in this simulation, numerical simulation shows such time variation of disk orientation. So this is a picture I took from Anglada 2020. So this simulation calculates this formation with the initial function where the rotational axis of dense core is misaligned with the magnetic field by like 80 degrees. So then they indeed observe time variation in disk orientation, and also they found misaligned two molecular outflows in a snapshot. But in this situation, they also found that the last initial misalignment angle is required for initial formation. If the misalignment angle is like moderate, like 50 or 60, then they did not observe like significant time variation of disk orientation. And similarly, in simulation of disk formation in turbulent dense core, some theoretical works also report time variation of disk orientation and time variation of output direction. So we are looking into dense core properties to figure out which picture better fits to our observation. So these magnetic field vectors, which is inferred from polarization observation, and this is seen in one line on 10,000 AU scale. So basically, this we assume that this emission traces the core motion from 10,000 AU scale. So actually, this orientation of magnetic field and velocity gradient direction highly depends on spatial scale. But assuming that this large-scale velocity gradient reflects bulk rotational motion of dense core, then we can get some idea about orientation of position angle or angular momentum vector on the plane of sky. And from polarization observation, we can get some idea about position angle of magnetic field direction. So these are the number inferred from this observation. So still, high misalignment like tested in simulation could be possible in this dense core. And we also check turbulence energy in this dense core. So using the same map, one is GSMD 850 micron contribution, and the other one is 801 line. So using this data, we calculated core mass and non-thermal velocity, and we calculated the ratio between turbulence energy and gravitational energy, and we got this kind of number. So main uncertainty here is assumed temperature to drive the core mass. But anyway, these numbers are much higher than the number used in simulations, which reports the time variation of disk orientation. So turbulence scenario could be also possible in this system. So finally, one more important interesting thing is that I also compared major turbulence energies different dense cores. So this vertical line shows the major value in IRS 153984, and histogram shows our measurement in Perseus dense core. So actually, turbulence energy is kind of typical value in this dense core. So if really turbulence for such time variations in the disk function process, then this could be a common event at very early phase of the star formation. Right, so I'm gonna stop here with this summary. Thank you very much.
Thank you, Shipping. So, questions?
Very interesting. So I'm just curious, what kind of time scale you would expect to change the direction of outflow? And then I also want to see, then whether we would expect to see also disk in a different direction as well.
Yeah, so regarding time scale, I honestly don't remember the simulation, but observation, so we estimate this kind of dynamical time scale, so difference between primary and third outflow, the dynamical difference in dynamical time scale, primary and third outflow is like 10 to 4 years, so it could be time scale of dynamical change of output direction. And from observation we can only get snapshot, but basically outflow should be ejected on this normal direction, so we should expect time variation of disk orientation as well.
But you see that this also different directions, right?
Yeah, right.
Any other question? Yeah.
Thank you. The core could be also an enfolding. How did you make sure that you're measuring the turbulence, not the enfold?
Yeah, that is right. But so in this case, for example, under here we don't see any inflow motion. So I just measured non-thermal velocity line widths at off position from the protostellar position. And in this histogram, yes, I think the inflow motion could be included, but even if we compare the measured value of this target and starless core, still is within typical value. So the starless core should not collapse yet. So.
Okay, thank you. I have a very quick question. So can you completely discard that you don't have very tight binaries inside the core?
Yeah, that is possible, but that is also possible. But for example, some non-binary with some large some binary disks only show like a very collimated outflow, and it's not that this kind of multiple outflow is not observed in very tight binaries so far. So I expect a different scenario now.
Okay, so let's thank Jinshi again.
Thank you.
Our next speaker is Sadoko Takahashi, and she will talk about extremely young protostellar jets in Korea and review with ALMA.
Thank you for the invitation from yesterday. And after 10 minutes, you have to talk a bit.
Okay, hello everyone. So today I'm going to talk about a very compact outflow from the very young protostellar source. So as many people presented the nice outflow and jet results, so these are very important to remove the angular momentum. And from the observational point of view, molecular outflows are ubiquitously observed, outflow having the wide opening angle and low velocity, while the protostellar jet is still limited in number. This is the review paper from the Jinpei. Before the ALMA start to produce more results, only like 7 jets are found observed in both SIO and CO. So due to the lack of the sample, the nature of the molecular jets are not well understood yet. On the other hand, from the theoreticians are discussing a lot about the physics of the jet. So we have to feed observational data more to better understanding the molecular jet. And with the ALMA sensitivity improvement, finally, this enables us to search for the fainter jet associated with the protostellar sources. So as presented by Dr. Johnston, a very nice seminar, there's also the Protostar monitoring studies, which is more related to the accretion side. And this is already paying negligible number of the source out of the protostars showing the variabilities with a period of a day, 2 years. So comparing this with the jet note, which has a time scale between a few years and 1,000 years, and investigating relation, so the jet notice may be related to the mass ejection side. So comparing this very important to understand the mass accretion and the ejection relation. So today in this presentation, I'd like to present a case study of the very young jet we have recently found from the ALMA observations. So target name is MMS1, allocated to the OMC3 region. This yesterday I presented. This is a 850 micron image obtained with the SMA, and we have found many interesting protostellar and protostellar cores. So in this region, there's many interesting targets, but MMS1 is located in the north, showing very compact structures. While going to the infrared observation, even at the 70 micron Herschel image, we don't see a counterpart. And before the previous observation doesn't show any signature of the outflow, no jet. So it means like this core, it looks like sharing more protostellar nature. So we were wondering what is the source, and we have performed an observation using the 1.3 millimeter continuum emission plus SIO and CO observations. So angular resolution we have achieved was 0.2 arcsecond, which is corresponding to APAU in Orion. So achieved noise level is something like this. Then what we found is very nice, very compact outflow and jet. So here the contour shows the CO outflows, and while the color shows the SIO. So CO shows the wide opening angle and the relatively low velocity outflows and gas, and showing the velocity less than 50 km per second. While SIO jets show the more collimated structure but also wiggling, and showing the internal like continuous jet plus bow shock-like structures. They show the velocity up to 92 km per second, so it's like really high velocity. So overlaying the 1.3 millimeter continuum emission, we also find a compact continuum emission now spatially resolved, and this elongation is almost perpendicular to what we see in the outflow and jet. And we used it to the Gaussian fitting, match component fitting, and we have found the compacted component can be fitted with the very compact disk-like structure, which has 43 AU times 26 AU. The inclination angle is estimated as 53 degrees. Assuming the dust component trace the disk-like disk, and we calculated the mass, the disk mass is still very, very small as this. So then we have calculated the dynamical time scale using the kinematic information collecting with the inclination angle. Then we have found the jet show the extremely short dynamical time, and outflow is also in the order of a few hundred years. So these are like outflow discovered found in the Orion region, or like other any nearby surrounding regions. So typically we see the dynamical time scale of the outflow is like 1,000 years or more than that. But what we have found, the source is having the dynamical time scale 1 to 2 orders of magnitude smaller than those previously reported. So it can expect a very embedded nature with very, very compact jet, means like very young phase of the protostellar source, probably right after the formation. So to better understanding nature of the jet, we also created the position velocity diagram. Here is the position and the velocity. And from this diagram, we found two distinct components. One is here, like associated to the edge of the outflow. And the second part is like halo-like structure, which means like the velocity structure, velocity goes up with respect to the distance from the center. So, yes, and so zoomed image here is this one, and we have successfully spatially resolved the velocity structure within this hub-like probe, and seems to have like several components, like the Hubble probe, but not only one component. At least we could see like 3 components. And just looking at the emission peak here, this one is not very clear, but somewhere here, edge. So this part is corresponding to the not detected in the SIO. This is the southern west part of the jet. So looks like so each ejection is corresponding to the historic event associated to the SIO. So the time scale to each node is calculated again because the jet itself is very, very compact. So to the node, the most close one from the center is only 5 years up to the 53 years. So if assuming that SIO emission is something related to the exotic mass ejection, so this intermediate mass ejection happens every 8 to 27 years. So this is very interesting. So here, so I summarize the PV diagram, what we found from that. So we have found Hubble flow-like velocity structures, and within this Hubble velocity flow, at least we have found 3 components. This spike-like structure showing the different slopes. And the first one goes showing the shallower slopes than the one ejected later. So to interpret this, we have also compared the result with the numerical calculation. This was based on the Machida and Vasu's paper. And we extracted the result from this data, the simulation data. And this simulation is resolving the very small size scale and producing the disk and outflow jet. So we can see the outflow and some episodic mass ejection associated with the jet. And we also created the position velocity diagram based on this data set. And so what I have to mention that here, it's very small number, the time scale is little, but because this has a very high resolution, we're focusing to the small size scale, associated time scale is very small, which is much smaller than what we are actually observing. But at least we can make the qualitative comparisons. And from this data set, we have found many similarities from what we see in the observation. The first, the spike-like structure in the PV diagram also was produced from the simulation, so we see like this kind of component, and it's like actually tracing much component. So then we can also see like the first ejection is already happened, and this is corresponding to this, and now the second component just ejected, this one showing like this. So the particle is accelerated now, but after some time acceleration stopped because they interacting with the surrounding material, and they started to decelerate. So they started to show the spatially extended, so it's moving to that, but also velocity goes down. So then they started to move this direction, but then a third component, the newest one comes and showing the acceleration. But the previous 2 mass ejection component is like deaccelerated and started to show the shallower velocity structure, like shallower Hubble-like flow. So as I mentioned, this PV diagram produced by this simulation share some similarities, showing the march ejection effect, which is seen in the also from the SIO image and also in the PV diagram. Also like showing this like different slopes ejected in the different time. Okay, second discussion is as presented by that very nice JCMT transient survey results. So he kindly provided us also the plot, but observing toward this source. So here is the plot time and the flux variation. So this is the light curve obtained in the 850 micron. As you can see, and this red point is the date our ALMA observation was done. So what we found is at least since here, we didn't see no drastic flux change for this target. So it means that there has not been a clear burst event within the last 8 years. But maybe monitor time scale is a bit still short because the node time scale to the first node is something like 5 years. So anyway, it's very interesting to see like what is going on. So we will probably observe another data point so this year, so we can see like how this like newly obtained image show or correlate with this kind of plot. So although the detection was very marginal, we kind of see like the tendency showing the decline in the brightness for this source. So that is something we found also. So here is a summary. So we have observed CO and SIO and 1.3 mm emission toward one of the 70 micron dark perimeter source, MMS1. And we have found very, very compact outflow and the jet. The jet has a less than 100 years dynamical time scale. And the evidence of the multiple exotic mass ejection was suggested from both observation and the theoretical side, the numerical simulation side. And the comparison between the SIO jet and the 850 micron flux monitoring implies there has been no clear burst event last 8 years. So this is the one case study, but we also have another interesting source, even showing propagation in the younger phase. So that's we want also start working on soon. Okay, thank you very much. Question for Zapata?
Is this the, sorry. This is great work. Okay. Is this the youngest jet ever discovered?
I believe this is the second youngest jet detected. And so actually this is the one I didn't present this time because of the limitation, but this is the probably the youngest one. Because if we look at the PV diagram, for this one, we only see the one ejection, like one half flow, not multi event. So also the comparing size of the MMS1 and the source, the MMS1, the internal jet is having similar size scale, but there is a bow shock outside, right? So it means like there may be like previous ejection in the large scale, so for the one present today. But this one is younger, yeah.
Great work, thank you.
More question for Satoto? Oh, sure.
I can just shop. I was just wondering, so those regions are covered by SMA in previous observations,
yes.
and including CO2 to 1, probably SIO.
Yes.
Has those outflow, if you go back to those data, can you identify outflows?
So for example, this source with the we detected this very compact outflow with the SMA, but once we observe the sub-arcsecond resolution. So the survey observation was something like 5 arcsecond. So because of the beam dilution, we never detect this kind of compact jet. So this is like the thing with ALMA, this is sensitivity plus like resolution effect, and we started to see this compact jet and all.
Okay, let's thank Satoto again. Our next speaker will be María, and he will talk about zooming on protostellar outflows, a combined JSW, JWST, and ALMA study of the very low mass class 0 protostar IL-16-253.
So, hello everyone, good evening. I'm Anglada. I'm postdoc at ASIAA working with Kagoshima. So today I'm going to talk about this protostar called RS16253-2429. So this particular protostar, RS16253, is a low mass, low luminosity protostar. which has been observed as part of JWST IPA program and as well as the ALMA large program EDIS. So the EDIS program, as led by Professor Ashisan, observed 19 protostars with an annual resolution of about 7 AU, both in continuum and light. So here I'm showing a gallery of EDIS results from Ohashi et al. In 2023. So these were recently published. And what I'm focusing on is this particular protostar, IRS-1653, which is a very low luminosity protostar. So it's a very low luminosity protostar with a luminosity of only about 0.2 Elson, volumetric temperature of about 42 Kelvin, so it's a class 0 protostar. It's relatively close by Ophiuchus at only 140 parsec. The star is, or central object is about 0.12 to 0.17 solar masses as demonstrated by Aso et al. There is a substantial envelope when compared to the stellar mass of about 0.2 to 1 solar masses, and the disk is quite tiny at only about 16 AU in radius and having a mass of about 0.002 MSun. Given the low mass of this particular protostar of about 0.15 and the relatively low envelope mass of about 0.2 to 1 solar masses, we can argue that the protostar, when it reaches the main sequence, eventually it will form a 0.2 to 0.3 solar mass star. And this is roughly where the IMF peaks, so this would be an M4, M3 kind of star. And these are also the stars that typically host a lot more exoplanets, especially Earth-like exoplanets in the habitable zone. So in order to study the bulk composition of the Milky Way, that is the bulk stellar composition of Milky Way, and also the bulk host stars in the Milky Way, it's definitely important to study the early phases of such protostars, such as IRS-1653. The ALMA observations not only detected a tiny disk, but they also showed a beautiful bipolar outflow. So this is from Aso et al., but this was also detected in Guillem et al. And Shigehisa et al. In 2019 and 2017 respectively. So we see a large bipolar outflow, which is about, here it's about 10 arcseconds, but in Spitzer it goes up to about 2 arc minutes. So it's a large outflow, but there is no collimated jet detected from this particular protostar. So this particular protostar was also observed as part of the investigating protostellar accretion or IPA team. So the IPA is a JWST cycle 1 gallery time geo proposal, which observed 5 class 0 protostars from ranging from 0.2 to 10,000 solar luminosities with NIRSPEC and MIRI MRS IFU covering the spectral range from 2.8 to 28 microns. So here we show a gallery of some protostars. Some of them are quite famous. We have B335, HOPS 153, HOPS 370, and IRS 20126. We also observed IRS 16253. So IRS 16253 is also called the vast space nebula. So if you look at the Spitzer IRAC 1, 2, and 4 image, you see that there is a very hourglass-like or hourglass-like shape. It's also very similar to the corsets that people used to wear during the Victorian era. So hence it got the name vast space nebula. And the JWST, we actually observed the inner 6 to 14 arcseconds of this protostar. And what we find is that the hourglass-like morphology also continues well into the inner 7 arcseconds or 6 arcseconds. Here in red we show the continuum, that is scattered light and dust. The green is molecular H2 emission, so this is the molecular emission in the H2S00, S119. So it's a line which has an upper state energy of about 5,000, 6,000 Kelvin. And we also see a very beautiful, highly collimated jet in iron. So if we separate out the components, this is the scattered light cavity, and this is the background star on top. So we see the scattered light cavity, we see the molecular H2, this is a different transition X9, and we also see the 5.34 micron iron line. And we see that there are some knots at the top and bottom, very symmetric, and the jet is about 400 AUs in one direction, so about 800 AUs across. So it's a relatively tiny jet with hints of knots on both sides. And we detect the jet in multiple iron lines. And this is the first time that the jet has been detected from this particular protostar. So these are all the iron lines, so this is 5.34. You can now clearly see the knot at 17.94 microns, also 26 microns. We also detected in the fine structure line of neon 2 at 12.81 microns. And very interestingly, we also detected in bracket alpha, that is the H1 transition for the bracket series. So earlier it was always hypothesized that the accretion rates we used to derive from protostars or even class 2 objects, we always assumed that all the contribution of accretion was from the central protostar. But JWST observations of not just IPA but also TMC1A, we have shown that there is a significant component of bracket or hydrogen lines, not just at the central protostar but also around the jet. And we also see that we trace the knot on top as well in the bracket alpha as well. So this is the first time that we detected a jet from this particular protostar. So now since we have detected a jet, we can do a lot more science with the jet. So this is like so what we find is that the northern side of the jet is blue shifted, while the southern side is red shifted. And given the MIRI MRS has a resolution of about 3700, that translates to about 40 kilometers per second, we can actually make a PV diagram and try to resolve out the velocity. And we find that based on the PV diagram, we have a velocity of about 169 kilometers plus 15 kilometers. So it's quite a fast jet, given that it's only a 0.2 solar luminosity object that's driving it. And you can see some of the structures that we see here are also seen in the reflected in the PV diagram as well. And with JWST, we also, for the first time, get the spatial resolution to resolve these ionic jets, so spatially resolve them out. So that's what we try to do. So we try to spatially resolve this jet. So you can see that we have enough signal records to actually resolve it out. And in the next slide, I'll show you the deconvolved jet width as a function of distance from the central protostar. And we see that as we move away from the central protostar, the jet expands with the width increasing from 23 AU to 60 AU. And the opening angle is about 22.6 degrees, so it's a very highly collimated jet. And we find that the jet width at the base is actually at least thankfully smaller than the diameter of the disk, which is about 32 AU. So it's been launched away from the disk. That made us very happy. And the opening angle of 2.6 degrees is quite narrow. And if you do a back of the envelope calculations for ballistic confinement of the jet, given that the velocity of the jet is about 170 kilometers and assuming a shock speed of 10 kilometers, assuming J shocks with temperatures of 10,000 Kelvin, we find that for ballistic confinement, the opening angle is about 3.5 degrees. So it's slightly larger than that. So maybe other confinement mechanisms might be at play, or we are just reading too much into it. So we also detect molecular outflows from this particular protostar. So here I'm showing the hydrogen H2S11 line. So you see, and in the center we show the disk from the E-disk observations. So 1.3 mm continuum disk. So we see that the disk is quite tiny when compared to the molecular H2 outflow, indicating that it's not just the gas disk, not just the dust disk, but also the gas disk from which the outflow might be launched. And when we compare this outflow morphology to the 12CO outflow, what we find is something very interesting. We find that the 12CO actually traces very well the molecular outflow from H2. You can clearly see that at the neck of the protostar or the outflow, you see a great match. There is some slight, but this might be just resolution effects. But in the southern cavity, definitely it's tracing it very well. But in the northern cavity, we find that there is a small bow shock, which might, because of which we think that the northern cavity has slightly different excitation conditions, and it's slightly, especially at higher excitation H2, it's slightly narrower, tracing a much more denser region. So once we have both the kinematics as well as the morphology of the jet and outflow, we can start talking about some jet protostellar physics. So here I show the spectrum of the protostar from 2.8 to 28 microns. We see a lot of these lines, so these are all legitimate lines. You also see that you might think that this is very bad signal here, but these are all actually genuine lines. So these are all the CO gas phase lines starting from R equal to 0 all the way to R equal to 55, and same in the P branch all the way to about R 52, 53, P of 52, 53. So really high excitation 12 CO in the gas phase. We detect several important ice lines. This is the 12 CO stretching mode. This is the 12 CO. This is 12 CO2 stretching mode. This is 12 CO stretching mode. You might not believe it, but this is 13 CO2. This tiny dip. So with JWST, we have just incredible spectral and resolution as well as sensitivity. We also detect some 12 CO bending ice. We also detect CO2 in the gas phase. We also detect OH, H2, but what we don't detect is H2O. So this particular protostar, we don't see any water, but we see a lot of OH. So what we hypothesize is that what is happening is that the water is getting dissociated with the UV from UV and is producing OH plus and OH plus and H minus. Given the mass of the protostar of only about 0.15 solar masses, there's not enough UV photons from the star itself to dissociate water into OH. So what we're hypothesizing or what we're proposing is that the OH molecules are being produced because of the accretion shocks, which can generate UV photons, and using the production rate of OH molecules and the emission rate of OH molecules, we can compute the production rate of UV photons, which can produce the mass accretion rate. And we find that the mass accretion rate for this protostar is about 2.4 into 10 to the minus 9 solar masses per year, quite tiny. And if we simply derive the mass accretion rate from volumetric luminosity, it would have been 2 orders of magnitude larger, indicating that the luminosity of the protostar is being dominated by the photosphere and not the accretion luminosity. Next, because we have extent line diagnostics towards the protostar, we actually compute the extinction along the jet, which tells us that the extinction rises towards the central protostar. We use the LTE formalisms for hydrogen, and we can generate rotation diagrams which we can correct for using extinction. So red is the observed rotation diagrams. You see the dip, which is because of the silicate 10 micron absorption. When we correct for this, we can get a nice, almost continuous rotation diagram telling us that the rough temperature of the gas is about 700 Kelvin, and we find that the extinction rises towards the protostar. And because we also have several iron lines, what we can do is we can do nomograms, we can use 1D shock models, and we found that there are certain good pairs, such as the neon 12.8 to 5.34 micron pair, and the 17.94 to the 5.34 micron pair, which are both extent velocity as well as shock density tracers. So we find that each of these apertures are basically color coded, and we find that so this is where the central protostar is. We find that the pre-shock density is around 2000 per centimeter, and the shock speed is about 52 kilometers. You plug in this into this formula, we get the mass loss rate from the jet to be about 10 to the minus 10. So if we put everything together and compare it with the other well-known class 0, class 1 and class 2 protostars from Watson et al. 2016, we see that ASIAA actually occupies a parameter space which has never been probed before with Spitzer or with any other telescope. So it's a low accretion, low mass outflow rate, suggesting that the protostar is in a quiescent phase. With this, I leave my summary and I'm open to questions.
¿Puedo hacer primera?
I was just wondering, you said you didn't see water, but I thought you saw water bending. Did you mean you don't mean it in the gas phase?
Yeah, we don't see it in the gas phase, we just see the ices.
Thank you.
So I have a question about the jet velocity. Are those jet velocity being projected, or?
Yeah, we correct for the inclination.
Is it like, what's the inclination? I don't know.
64 degrees, so it's quite high.
I have a question regarding, you showed the bracket alpha.
Yes.
That usually these lines are used to estimate the accretion rates of the star, right?
Yes.
So in previous observations, people are assuming that all that emission is from accretion. So does this mean that the accretion rates and the accretion luminosity are overestimated?
So this is what we are thinking about. So we know that the jet outflow rate and the accretion rates are correlated. So in a sense, we're still measuring, like even if you're measuring the entire jet luminosity of let's say bracket alpha or even let's say H alpha, we're still, I think, in a certain way accounting for it because we're measuring the entire jet, and we know that the jet luminosity is equal to is proportional to the accretion luminosity from all the fraction papers and all. we know that there's a correlation between outflow rates and the accretion rates. So even if we are overestimating the H1 flux, we are still, I think, relatively okay, but we definitely need to prove this with a lot more larger sample.
Okay, thank you. Let's turn María again. So our next speaker is Jesús, and she will talk about a holistic approach to the understanding of protostellar jets and outflows.
So this is my topic. What's the approach to protostellar jets and outflow? In addition, I'm going to. This is actually two talks combined to one because I'm going. This is celebration for Paul's long career in HIA, and then things I'm talking about legacies Paul. So this is a catch up for finally I got a photo with Paul. So that Paul, congratulations. Okay, next we talk about frame because in terms of jets and outflows, we cannot avoid talking about legacy of Frank. So there's a web page in HIA for memory of Frank. So we are talking about intertwining the legacy in HIA. So this outline, I'm talking about class 0 phase. In the end, I got Frank to accept class 0 phase. Okay, he has to accept that if he doesn't he want to accept the jets detection from Qingfei. Okay, next is we're talking about how we do from X-rays to jets and outflows. Then we're talking about new diagnostic of the observation we have seen so far, especially the new nested shell and kinetic structure from ALMA and other combined with many things. And this presumably can last from class 0 to 1 to 0, 1, and 2 plus. So what's the physics implied and potential outlook? So this is what people think about the outflows like. So you have a jet and you have something going on when it's driving from the source. That many people have talked about in this section. And then what the key is, while we can trace this outflow load, we know the jet and what's inside, what's driving all the emission features that we detected. Next, this is the long history back to Snell et al. When people start to detect emission lines and we see and there's a slow moving outflow shell and to both directions. But it was envisioned that something like a wide angle spherical stellar wind is driving as an indication of the star has in formation. And this is new results in a new later picture from Paul Riper using Subaru, but we see that it's actually not empty, and it's full of shots. What's going on? Now, we review a little bit the intertwined legacy of jets and outflows. So this is a jet from Toroid stars that's taken by HST, and we know this is a famous Toroid stars, and we know other cases that's there. Then here's an X-ray model that people like to talk about or don't like to talk, but here is what it is. So, because the star will have to become its magnetosphere at some point, because the primordial magnetic field has to detach from accretion at some point, because otherwise you cannot form a star here. So this is what's going on in steady state, but it doesn't mean nothing happens with variability done. So in steady state, you can find a structure like this that's an inflow going on, outflow going out. And it's we can define a truncation radius coinciding with polarization radius coming from the gravitational potential around it. So it's called the X point. It's a gravitational X point. And we can calculate steady state. The mass outflow has to be lost through the X point. The X point is not really a real single point because it's mathematically simple for a solution, but in reality, it definitely has some width. So you can get a fraction, you can define the mass loss rate out of mass accretion, so the star accretion can come onto the star via the loss of mass. So this is the picture of this formation of jets that by magnetic group stress on the large scale, it will be collimated cylindrically, so it looks like a jet but while the wind is coming out as a wide angle, at the widest angle you can get. And this is a temperature, a velocity structure, and we see the kinetic structure of the wind coming from wide basin collimated in the long distance. Now, here's what Paul had been trying to do with me. So in the early days, I did submit a failed HSV proposal with Paul and to detect the jet structure. But after that, he set up with me, with Jennifer, so we did succeed with the HSV proposal cycle 10. And there, so we did imagine that we can detect many things. Jennifer, hopefully, with new model, we can detect more. So this is how Paul's getting me into optical astronomy. Okay, so this is for the Mafia. We did also attempt to model free wind. Okay, so this is all the other lines we did. Neon 2, Sapphire, Neon 2 and 3, and many things. Okay, now this is the continuous path for optical astronomy that Paul got me into, and I just couldn't stop it. Now, so what do we have to do with a cluster source? So what do we do at ASIAA? So this is collected the 3 most studied outflows that ASIAA started, and H211, 212, 14488, that people actually heard some from the earlier talks. So what's special from this H211, which was at that time the youngest outflow source, is that we detected the kinetic structure that we connected all the work from Naomi 2006, done by SIO 524, Anna, done by 322, SIO 827, and we actually detected the jet component and the envelope component, and we actually can see that how the jet is actually following similar behaviors as the optical Toroid jets. And it's actually showing the right behavior while thing and going down up. Then what's going on? And if you actually follow that SIO 827, CO22, when you go up to the excitation line, you see denser material, and this is our work together with Naomi and Qingfei. We probe this SIO jets all the way by changing configurations and resolution, and we end up this very high angle, very thin jet, but still the jet's unresolved, right? Because it gets narrower and narrower as you go with resolution. And however, we can actually set from the estimate time the launching radius for this H211 about 0.15. This is the first detection of jet rotation from such a small radius, which could only be possible by X-ray jet. And this is the story about 212. So Qingfei continued, and their improved resolution, and from this is alpha at different configuration and continue on, and Qingfei continued to study the surrounding material, surrounding aluminium, and they actually follow the famous hourglass shape threading through the pseudodisk. And this is the inner part. You do have a capillary disk and covered within the pseudodisk. And this is the time cavity surrounding SIO jet as resolution improves and configuration improves. And this is also about 1448 that Naomi was studying. And so this is the same thing. And actually in the early days, CO322, we already see the jet behavior showing right here in cavity structure. And it actually, for the ALMA results, it actually shows very intriguing results that's continuum. Now we will explain the later sections. So this is SIO827, and then we see the jet component with wide velocity dispersion, narrow up along the jet axis. So this is a detection, the only existing detection of line polarization when you have predominant protoid magnetic field around the jet. from H211. So what does it tells us? And Qifei actually had another one that's in an SIO jet for H212, where we actually could model with our X-ray solution, a syntonic solution. It's following this message, structure, but it's actually, so the jet is really cylindrical stratified and would write expected kinematic structure. So what does it tell us? So it tells us that the jet outflow from low mass stars actually continue on from T-Toroid star to class 0 sources. Okay, so what I'm going to talk about unifying framework of the Protostellar outflows, because I'm under the influence of this Reverend Xu, who likes to have everything unified. Okay, so here's the formation process of solar system like our own, and we think it's probably the jet is surrounded by this ambient magnetic field, and this is a simulation result, and then we can actually have the outflow form this way. Then this is already theoretical predictions that made by Daniele Galli, that we can produce pseudowaves from the collapsing cloud cores. So this is the sun's cloud disk, and this is a jet, and that's an hourglass shape. So this is this prediction was confirmed by first polarization result done by Raymond Brown, which is done by SMA. I didn't have a slide here. So then this is a theoretical version of the process. You have flux, magnetic flux going on. You form a large steel toroid, and you form a pseudogenesis inside. And then the expansion rate going outwards, and the field lines form hourglass edge. So, and then now, how do we form outflows? So we know Xu et al. 1991, who proposed a thin shell model, a momentum conserving thin shell model, to explain what's happening at Snell et al. So what they coinciding with the imagination from Snell et al. So where we can have parameterized the process with a density from the surrounding cloud core and then a momentum from the star. So this is a parameterization with a vector simulation, a jet, and right angle with with stratified density profile. So this is doing this at any time. Then we simulate the process. We can produce the QE diagram like the SIO and CO and the SMA, which are all sweeping. So what do we do in ALMA? Okay, so this is the wide parameter space. We set up with things with a much higher than numerical resolution and the different wide parameter space for magnetization for the wind, for the cloud core, for the cloud, and for other things. So this is just a partial set of simulation. So we see that we form outflows this way. So to our surprise, that it actually formed a variety of morphology and structure by varying this parameter, and we can go from highly magnetized to low magnetized region. So this is we only have hydrodynamic simulations, and we have different variation ambient and wind parameters, wind magnetic strength. So what does it do for ALMA and beyond? So same thing. We transform a molecular energy outflow from simulation into synthetic images, and this is a thing that converts synthetic observation. We convert that to precision velocity diagram. What is happening? Okay. Before that, we realized from the simulations, things do not follow exactly what Xu et al. 1991 predicted. So actually, this is the one that should be closest to Xu et al. So yes, we do see kind of thin shell, but we see other structures coming out. But otherwise, we see a structure contrary to what the hydrodynamic simulations would predict. So we predict thick magnetized in left. And we predict highly stratified velocity distribution and nested. So this is This is a systematic observation with the column. You can see, for example, for one set. So we see that we form nested shell structure, and we see nested pulses. And real true or not, but we didn't have a real ejection. But it forms naturally within the outflow. And what's going on? So we see the nested structure around H212, and especially this will form with the H46, 47 outflow, which is really shown to be nested, and we can actually recover that jet is embedded inside the shell and the structure. Then what's going on? So this is what's going on. Then in the 1991, we have been shown momentum conserving model. So everything is still momentum conserving. But now we have another one following 1992, 1 year after Frank published this famous paper that Chris McKee and Curiel and McKee published another one that goes to, that actually used in the wind-driven evolved star and supernovae community, which is a wind bubble structure, which means that when wind blowing into the median, you actually form a very thick compressed wind region inside here, but bounded by reverse shock and then separated by contact continuity from the ambient shock, which we usually take the outer boundary, the magnetic outflow. Now, here's the diagram. French was or Christmas key was right. Okay, so here's a reproduction of thin shell simulation, which follows perfectly what Frank predicted. But this is our magnetized simulation. We actually observe many new phenomena that actually we can form multi-Rs, that's the interaction between the ambient magnetic field and the ambient median. We form reverse shock cavity, which is trace tiny trace inside here. We form column compost instability fingers that's extended outwards, and we form a very thick extended region and compressed wind. And this is then we see the pulses. We call it pseudopulses that's forming and imitating the shell and multiple ejection phenomena people were reporting. Okay, this is skippable. And now this is a physics. So that means when the wind blows out into the medium, we form a shock structure like Chris McKee predicted, or Chris McKee couldn't be wrong at this point. But again, Frank was correct too. It's also momentum conserving because the outer shell does follow momentum conservation trajectory. Both were correct, but both missed something. So this is an elongated bubble that Chris McKee, Curiel McKee never predicted. But when it's elongated and it's magnetized, a new range of phenomena just appeared. And that's what happened. And in particular, when the wind goes through the reverse shock, which is oblique in every angle, it actually changes the full direction. And that gives you a new sense of layer of wind surrounding the primary free wind. And when you extend the foot point, it appears outside the original launch point. This is just like the water light. The light goes through water when you have a different index. Refractive index, you change the direction. When you project it, you can never catch fish if you just go straight line. So this gives people a new set of wind is coming out surrounding the primary wind that people usually interpret a second energy slow wind surrounding the jet. Okay, so that's what we combine all the physics from Frank Xu to Chris McKee, and then we renovate it with magnetic field, because we detect magnetic field. The speed we predict jets is driven by magnetic field, and this is what's going on. and we think this explains many new phenomena, H2 and 2, and this thing. So this is our new imagination of outflows happening. That is more, it's big, you have very extended structure, so the cavity is no longer empty, it's full of shocks and machine shocks. And then with the flow that's coming out, looking like giving multiple velocity components. And importantly, most importantly, it's thwarted it's thwarted by magnetic field, which we have indications of such results. I don't have time to go through H30, so when we interpret H30, then I think we think H30 combining our result data archive of our HSD proposal and new and ALMA archive, we produce a perfect example for atomic wind driving material ambient molecular material. Yeah, thank you.
We are running late on time, so just take all the theoretical messages that Sheni has told us, and then if you want to discuss with her, you can take tomorrow or the day after. So let's move to Natsuko Izumi. She will talk as a change web observations towards the star-forming clusters in the extreme outer galaxy.
Hi, I'm Natsuko Izumi, a postdoc at ASIAA. So today I will talk about the overview and preliminary results of our DWST observations for the star clusters in the extremes of the galaxy. Okay, let's start with the direction, and I think I should talk about what is the extreme of the galaxy. Here is a very famous picture of our galaxy. And if you imagine the galaxy, in short, EOZ is outside of this circle. But why of this galaxy radius is so important? Important is that this region is outside of the spiral arms. So the EOZ has a different environment in the solar neighborhood and in the galaxies. So for example, this approach shows the H2, H1 total gas density variation with galaxy radius. And all values at EOZ is less than 1/10 of the solar neighborhood. And also this approach shows the metricity variation with galaxy radius. And metricity EOZ is about 1/5 of the solar neighborhood. And this value is exactly similar to the small magnetic world. And so, so the EOZ has similar characteristics with the galaxy, and we have the R phase of our galaxy. So this is the alien metricity relationship in our galaxy, and the cycle indicates the metricity of other galaxies. So those are reasons I'm interested in this environment. So my question is the Frankel cloud and storm properties in the EOZ are same as those in the disk or solar neighborhood. So it means that the Frankel cloud and storm properties are universal or sensitive to the environment. And the properties including the mass function, structure, Astrometric rate efficiency, and evolution. And I'm also interested in the trigger mechanism of star formation of this region because there are no spiral arms in these regions and there are very low gas density in these regions. So to investigate these questions, we performed the near-infrared to mid-infrared imaging observation of two star-forming clouds located in the EOZ. The name is cloud 1, cloud 2 with DWST. And here I show basic information of the two targets, 1 and 2, and location of the target. And Based on our previous observation with SMART telescope, we detected 2 star clusters in each target. But I also noticed that the mass of cloud and number of so it's not so big, so I mean that there are no massive forming clusters. Some region is in the target. Here is a more detailed information about observation settings. And we use 9 filters from 1.15 microns to 21 microns. And I set the sensitivity of this one. So this sensitivity is roughly same as the white sensitivity at Orion. So this observation will enable us to compare the property of sample regions in the UOZ and Solar neighborhood with same sensitivity for the first time. And here it shows field of view of the observations. Left one is the cloud 1, and right one is the cloud 2, contour is the micro cloud. And so for the class is located here, 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 and here, and the Sian square and Modena squares indicates the field of view of the near term and very here. So I want to move on to the result, but I'm sorry, I should note that. So this is the preliminary result before submitting paper. So I should ask you to not take a photo for all data with the image. Sorry. Okay, so sorry.